Everyone, and welcome to this lecture of Advanced Geodynamics, Theory and Modeling. In the previous lecture, we've discussed the derivation of the heat equation, which is a central equation in geodynamics. It's being used, for example, in the simulation of mantle convection, or to derive, for example, the thermal structure of plates, being oceanic plates or continental plates. It can also be used to study contact metamorphism to understand how heat supplied by the magmatic intrusion is affecting the surrounding rock volumes. And it's, of course, a central equation when it comes to the study of geothermal processes. This equation takes the form of the diffusion equation, which relates the rate of change of temperature to the Laplacian of temperature when K, the thermal conductivity, is considered as constant with regard to space. To derive this equation, we have made sure that the entropy production is positive, and in order to construct the entropy production term, we had to supply a formula for the heat flux, and this was Fourier's heat flux. So altogether, this equation satisfies the conservation of energy, the non-conservation of entropy, which has a positive production rate, which includes the effect of Fourier's heat flux. So can we use the approach we've used in the previous lecture to derive more complex set of equations for geodynamics? And the answer is yes. And what we're going to do today, we are going to start with coupled processes. So in geodynamics, we have many types of coupled processes, and one type of coupling is thermo-chemical coupling. For example, systems in which temperature and concentration are both diffused and advected and also interact with each other. So that's an example of a magma chamber dynamic simulation in which you have an evolution in space and time of temperature and also an evolution of space and time of the concentration of water. This example is now at the scale of the mantle, and that's a mantle convection simulation that accounts both for the diffusion and advection of temperature and composition. You can see a time evolution here and the formation of a stratified mantle here in terms of temperature, but also in terms of the composition. So that's one type of coupling. A second type of coupling would be the hydrothermal coupling. It's highly relevant for geothermal processes, for example, to study porous thermal convection in reservoirs. So if you want to understand how porous rocks, which are subjected to a geothermal gradient, how they conduct fluids, or if faults are affecting fluid transfer in any way, you can use hydrothermal couplings. This is something we will consider the next week. And that's, of course, central to geothermal processes and energy, and these are examples of 3D structure of the subsurface reconstructed here and associated 3D modeling of the temperature field in the subsurface reservoir. So this needs to account for hydrothermal couplings. A third coupling would be the thermo-mechanical coupling. That's key for mantle convection, but also to study strain localization and lithosphere dynamics. So that's picture is already a picture I've shown a couple of lectures ago, which shows the generation of strain localization in a heterogeneous material subjected to pure shear deformation. So from the background pure shear deformation, you evolve into local simple shear, localized shear zones. And this model can be applied to the study of subduction initiation. So you have a similar model configuration, except that here you have an oceanic plate, a continental plate. It's subjected to compression from both sides. And then you see here, these are isolines of temperature. So you see the isotherms that are rising up. This is the sign of viscous dissipation taking place and strain localization. So these couplings are all important. What we're going to focus on today is the chemical coupling, and what we're going to address in the coming weeks are the hydrothermal coupling and the mechanical coupling. So in the thermochemical coupling, we want to consider a single component system, and we are going to have both a temperature field and a concentration field that will diffuse. So we need to construct equations for the evolution of both of these quantities, and these equations should be thermodynamically consistent. So we have to respect the conservation of energy. We have the first equation here, and now since we have a composition field or concentration field, we are going to have a conservation of the concentration also. You can see the structure of the equation is basically similar, just U is substituted by C. In addition to that, entropy still should be produced, so we have this non-conservation equation of entropy. So the balance law of entropy still applies. So let's start with an entropy check, and now we start with formulating the differential for internal energy. So this you can recall from the early lecture. du equals TdS minus PdV plus mu dC. This term, we have not been considering it so much in the previous lectures. So we recall that mu is the chemical potential and C is the concentration. In fact, that's this type of coupling here. So we change the internal energy of the local system by changing the concentration here. To simplify things, we are going to neglect volume changes. So the PdV term will disappear. Now, this equation is simplified. du equals TdS plus mu dC. And let's formulate a differential for entropy. And we're going to formulate it using the previous equation. So du equals TdS plus mu dC can be solved for ds. And this gives 1 over T du minus mu dC. In the second step, we'd like to express this differential of entropy also as a function of the temperature change. So we are going to express du in there using a total differential as a function of temperature. So du will be written as the partial derivative of u with regard to T at constant C times dt plus du partial derivative of u with regard to C at constant T times dC. Now one can identify that this here is the heat capacity du dt at constant C, and this du dC is the chemical potential at constant T. So we can simplify this relation here and inject du into that expression. So we get ds is equal 1 over T times Cc dt plus mu T minus mu dC. To simplify things, we are going to assume that mu and mu at constant temperature are actually the same, so this term is going to cancel out. That's our differential of entropy for the following of the lecture. We will have Cc over T times dt. Now, let's start deriving the entropy production. For this, we start with du equals TdS plus mu dC, and we solve for TdS. So we repeat the steps before, and we express now the balance of entropy and solve the balance of entropy for TQS. So if we solve for TQS, we obtain T rho ds dt plus T divergence of QS. Now we do one more step. We multiply here everything by rho, So we have rho TdS equals rho du minus rho mu dc. Rho TdS is already in our equation for TQS, so we will be able to substitute this by that. Let's do it. So we inject now rho du dt minus rho mu dc dt into the equation for the production of entropy. So what are we going to do now? Now we have to identify the different terms. We have du dt in this equation, and du dt can be replaced by minus divergence of Qu using the energy conservation law. So we are going to substitute du dt by minus divergence of Qu. There is also another term here, which is rho dc dt. What about this term? What can we use there? Remember, now we have a concentration conservation law, and we are going to be able to substitute rho dc dt by minus divergence of Qc. So let's do it. Suddenly everything becomes simpler, but not for long, because now we realize that we have the divergence of Qu and mu divergence Qc plus T divergence Qs. What we want to do now, we want to generate a big divergence term. So we are going to work on the different terms to generate a big divergence term, as we did in the previous lecture. So let's do it with these terms here. You see that we have the product of a quantity times the divergence of something. We can apply the product rule to each of these products to generate divergence terms. Let's do that. In the first stage, we apply the product rule. This here is nothing else than the divergence of mu Qc minus Qc times gradient mu. So this generates two terms here, and we do the same for this product. This gives us the divergence of TQS minus QS times gradient T. Yes, it just fits here. Now, let's start gathering divergence terms together. So we can cluster the different contributions from Qu, mu Qc, and TQS in one big divergence term. And we are left with production terms that are here. So the divergence term, remember, it's quite important here because the divergence term is a term that should not produce any entropy. So this term has a negligible contribution to TQS, and we need to cancel it out. There are different ways to cancel it out. One can say that the whole term, the divergence of this whole term is 0, or one can say that directly the term here, the sum of these vectors here, is equal to 0. And this is what we are going to do. This is the simplest choice, and we are going to say that TQS plus mu Qc minus Qu is equal to 0. This is important because it will define the relationship between Qu, Qc, and Qs. So the consequence here is that Qu is equal to TQS plus mu Qc. Now we should keep that in mind. So it will be written here in the corner. And we can simplify the entropy production. TQS equals minus Qc gradient mu minus Qs gradient T. So what we're going to do now, we're going to make everything positive. First, we start exactly solving for Qs. So we divide everything by T. And we are going to inject some fluxes that will make all the terms positive. First, let's suggest that the entropy flux is proportional to Fourier heat flux. It's 1 over T times Fourier flux. So Fourier's flux is minus K gradient T, and obviously if we inject Qs as 1 over T times minus K gradient T in this expression, we will generate a positive term because the minus sign will cancel out, and the occurrence of gradient T times gradient T will produce gradient T square. This is similar to what we did in the previous lecture. So we've generated a positive term here for the entropy flux, the contribution of the entropy flux. Now we need to care about this term here, how to make this term positive. So here it's a bit more tricky because we need to consider the chemical potential. In fact, the chemical potential can take different forms, and in the case of an ideal solution, chemical potential is actually not a simple function. It's a function of a reference value, but it's a function of T and C. So if we take the gradient of this, the reference value will cancel out, but we will, and R is a constant, it's the gas constant, so we'll have R, the divergence of T log C. So this is, will expand into two terms, obviously, and the gradient of mu will include a term which is function of the temperature gradient and function of the concentration gradient. So for the time being, we will make an approximation, and we will not consider this term here that produces the cross term between the gradient of temperature and the gradient of mu. So we will consider that gradient of mu is simply this part here. So we neglect this contribution. So gradient of mu is RT divided by C, gradient C. We do it here. So now suddenly we have R divided by C, T divided by T has disappeared, and we have the gradient of C that multiplied the flux C. And now what we can use is again some knowledge from the Fick's law. The Fick's law states that the chemical flux would be, or the concentration flux would be a minus D, so it's a positive coefficient, times gradient C. If we use this into this formula, what will it generate? Obviously the minus signs are going to cancel, and the gradient C will be made square. So we end up with R being a positive coefficient, C is a concentration, it's positive, D is a positive diffusivity coefficient, and gradient C to the power 2. So now we've derived an entropy production which is positive. So in order to get there, we had to combine two expressions from fluxes, like historical expression for fluxes, and we need this combination to make everything positive. So that's already a great achievement here. Now the question is, what can we do with this? Can we already do some modeling? And the answer is unfortunately no, because we still need to get expression to predict C as a function of space and time, and T as a function of space and time. So let's derive equations for this. First, we start with the concentration. So we will start with the conservation equation, rho dc dt plus divergence of QC. Remember, we have an expression for the chemical flux here, minus D divergence of gradient of C. So let's substitute this into this expression, and suddenly we already have the expression rho dc dt is divergence of D gradient C. So in fact, we are already done. We have an equation that relates the changes of C with time to the changes of C with space. One can make an optional step here to assume that D is constant. It restricts the predictive power of the model, but it can be used to make it very clear that this is the Laplacian of the concentration. So the divergence of the gradient produces now the Laplacian. So the equation is simplified at most, and it can be used to predict the changes of concentration in time and space. Now we did an equation for temperature evolution, and we don't have a conservation law for temperature, so we need to derive an evolution equation for temperature. Let's start from things we know, which is the evolution equation for entropy. So what we know so far, remember, we've derived ds as Cc divided by T times dt. So we have the relationship between the rate of entropy and the rate of temperature. This is key here. What is also essential is the expression of Qs, which has a contribution from entropy flux and chemical flux. We have the expressions for Qs and the expressions for Qc. All of this will be used in the derivation. So let's start by introducing the expression for ds as a function of dt. So rho ds dt becomes rho cc divided by t times dt dt. That's the first step. Second, we're going to inject the expression for Qs. So we substitute Qs by the expression of the entropy production term. Then we will multiply everything by t. Why do we do that? Because you see in this equation we have division by t, division by t, and division by t. It's going to look better if we multiply everything by t. So the diffusion disappears from here, there, and a multiplication by t appears in front of the divergence of Qs. Now we can use the product rule. You see this term here, T divergence Qs and Qs gradient T. It's nothing else than the divergence of TQs. So we can substitute this into one term, and the equation is already quite simplified already. Let's now use the expression from the entropy flux, minus K divided by T times gradient T. Of course, the division by T, since now it's multiplied by T, it's going to cancel out, and we end up with K gradient T inside the divergence here. What's left to be done is to introduce the expression for the chemical flux. So we can introduce now the expression for gradient mu and Qc. This generates the production term that we had earlier on. So now there is a last remaining step. It's completely optional, but again, one may assume that K is constant in space, and in that case, one will obtain this equation with the Laplacian of the temperature. So that's an equation for the evolution of the temperature in the system. It features the Laplacian of temperature as we had last time, but since now we've been adding a coupling with another process, we also end up having a coupling term here. It's a Thermo-Chemical coupling term. So there will be a contribution of diffusion of concentration into the evolution of temperature. So that's a consequence of coupling the different physics here. So altogether, we have the equation for the evolution of the concentration field, and we have also derived an equation for the evolution of the temperature field with time and space. The result of this coupling is that we have a production term in the temperature evolution equation, which is linked to the diffusion of concentration. So with this equation, one may start to be able to predict now evolution of temperature and concentration in space and time. So we are making one step towards the possibility of constructing such a model, and also making one step towards the possibility of constructing models that may be useful to predict the internal structure of the Earth by coupling mantle convection with concentration evolution. So that's the end of the lecture, and have a nice day.